Hello everyone, I'm Alex. I'm working at X5 Retail Group. It's the biggest retail company in Russia, and I do everything that related with A/B testing. And today we're talking about linear models, CUPED, and how they are related. Since we are on advanced sector of A/B testing, so you're supposed to know what is CUPED and how it works. But if not, I suggest you to read some papers or read some articles, maybe watch some videos. For example, this method is described by Valery Babushkin. So in short, CUPED is a variance reduction method that can you help do your A/B testing faster or more accurate. So let's consider an example. For example, as usual, we run an A/B test and we have two groups. Control is represented as blue line and treatment that represented as red line. So as usual, we can compare them on average. For example, we can set a null hypothesis that their mean are equal, and we see that on significant level 5% we are not able to reject this hypothesis because p-value is equal 0.08. So but this data was generated by me, and ground truth that there are a difference between them. So the problem in t-test that was used in this case, that this test isn't sensitive enough. So the method CUPED worked when you have additional data. Usually it's your historical data that is correlated with your data in test. So how does it work? You can use this correlated series as a baseline and subtract some kind of prediction. And the main advantage of this method is that it's an unbiased method. So the delta between your groups are the same, but variance becomes lower. So you can see that the delta is the same, but p-value decreased by 10 times. So it means that our test becomes more sensitive. Okay, as I have already said, we are on advanced sector. So first part is devoted to math, and I hope you will not get bored because the most interesting part in the end. So let's start. Let's say we have a finite dimensional linear space. It's a vector space Rn, and then we can introduce the scale product. If we have a scale product, then sometimes scale product generate a norm. It's a good case, right? We can introduce a norm, and if we have a norm, then we can introduce a distance between two objects. And also we'll talk that two elements are orthogonal, or two vectors are orthogonal if their scale product is equal to 0. Okay, and today we'll talk about the best linear approximation, and this is just for interpretation. What does it mean? Let's we have some subspace L and the vector y, and we want to find the best approximation of vector y using the vectors from this linear space. Let's talk about it. First of all, we want to give a definition. What does it mean, the best linear approximation? Let we have some closed subset of L and the element y, and we say that element y hat is the best linear approximation in the set L if two conditions met. First of all, the first, if we find the best linear approximation in set L, then the target element should belong to this subset. And the second, about the best. What does it mean? It means that our target element is no further from element y than all possible alternatives from subset L, right? It means that if we consider all elements in subset L, our target element is not worse than anyone else. Okay, I think it's a very clear definition, but unfortunately it's not a constructive. It doesn't answer on the question, how do we find the best linear approximation? At school, this method is called as Pythagorean Theorem. At university, this method is called as orthogonality principle, and it claims that element y is the best linear approximation of the element y in linear space L if and only if two conditions met. The first is the same, and it claims that if we find the best linear approximation in space L, then this element should belong to this space. And the second one claims that it's the orthogonal projection. What does it mean? Let's show in interpretation. Let's show a graphic interpretation. We have the same task. We have some element y, and we have space L, and we want to find the best linear approximation y hat in set L. So each element can be represented as sum of two vectors. First vector is the best linear approximation, and the second a height. But what does it mean that it's a height? It means that this vector should be orthogonal to any vector in subspace L. But what does it mean that this vector is orthogonal? It means that a scale product of height on every element from space L is equal to 0. And it's the way how we can find the best linear approximation. Okay, let's introduce some more definitions. First of all, about scale product. Scale product is a numeric function from two variables that satisfy the following conditions. First of all, if we find a scale product of element on itself, then it's non-negative and it's equal to 0 if and only if element is equal to 0. The second is linearity, and the last one is a commutative property. Okay, This is the last definition. It's the definition of Gilbert space. You can read it. Gilbert space is a linear space with scale product that generate a norm. So, and we need a Gilbert space because orthogonality principle can be used only in Gilbert spaces. So previously we considered some finite dimensional vectors, and it's just a Gilbert space. Let's consider now not a finite dimensional vectors. Let's consider random variables, and let's try to introduce a Gilbert space in only this space. We will consider not all random variables, but only such random variables that have a variance, and it can be shown that yes, it's a linear space, but we want to create a scale product that generate a norm. Usually when I ask somebody how to introduce a scale product in random variables space, usually they answer a covariance, but it's not the best choice, because let's consider an element, for example 5, random variables 5 with probability 1, it's just a constant, and obviously 5 isn't equal to 0. But if we find the covariance of random variable 5, it's a variance of constant and it's equal to 0. So one of condition is not met. Our random variable is not equal to 0, but scale product on itself is equal, and it's bad. But fortunately it can be introduced in other way, and we say that a scale product of two random variables is equal to mathematical expectation from product of two of these random variables, and it can be shown that all properties are met. Okay, moreover, this scale product generates a norm, and it can be shown that L2 is complete with respect to such convergence, so it's a Gilbert space. And also we'll talk that two random variables are orthogonal if their scale product equal to 0. And so if now we know that it's a Gilbert space, then of course first of all we want to find the best linear approximation. This slide is almost completely the same, but we will talk about it again to everything would be clear to everyone. Okay, let we have some space. Previously it was an finite dimensional space of vectors Rn. Now it's a L2 space. It's a space of random variables that has a variance. Yes, and we have some subspace. Also we have an element eta from space L2, and we want to find the best linear approximation of element eta in subspace L. So then we will talk that random variable eta hat is the best linear approximation of random variable eta in space L if two conditions are met. The first one is the same, they both are the same. So the first one, if we find the best linear approximation in space L, then our target element should belong to this space. and the second one about the best property. What does it mean? It means that from all possibilities from space L, our target element no further than any other element from L to our initial element. So okay, it's the completely same definition, but it doesn't answer on question how do we find the best linear approximation. Again, to answer on it, we will use a orthogonality principle, and it claims that a random variable eta hat is the best approximation of a random variable eta in linear space L if and only if first is obviously, and second condition claims that it's the orthogonal projection. What does it mean? It means that the height is orthogonal to every vector, to every element from this space. Let's show it on graphic way. We have some random variable and we have some subspace. This random variable can be represented as sum of two random variables. First is the best linear approximation, and the second is a height. What does it mean that it's a height? It means that this random variable is orthogonal to every element from space L. And what does it mean that they are orthogonal? It means that their scale product is equal to 0 for each element from this subspace. Okay, it was a theory, and now let's go to practice. Let's say that we have two random variables, eta and xi, and we need to find the best linear approximation of the random variable eta using the random variable xi. But let's do our task slightly more interesting and add to basis a constant random variable is equal to 0, and we will find the best linear approximation of a vector eta on subspace that is generated by two vectors. First is xi and the second is 1. So our target, the best linear approximation, can be represented as a linear combination of these vectors, and all we need is to find these two constants, c1 and c2. And to do it, let's use an orthogonality principle that claims that height should be orthogonal to every element from L. And we know that L contains from two elements, 1 and xi. Let's write it. The scale product of height on first random variable that is equal to 1, and the scale product is a expectation from product of these random variables. Let's open the braces and equal it to 0. And the next one is the same. The height is orthogonal to second random variable that is equal to xi. Open the braces and let's say that it's equal to 0. And we have two equations with two unknown parameters. So it's just a simple system of linear equations that can be solved anyway as you like. So of course we will not do it right now, and so it's the answer. It's the answer for c1 and c2, and then the best linear approximation is equal to mean of element plus some constant multiplied by deviation random variable c from its expectation. Let's look again at what CUPED is. Here is a screenshot from their paper where it is written that new time series is equal to old time series minus theta multiplied by deviation x from expectation x. And if we replace theta here, as a result we take this formula. So new time series is equal old time series plus some constant multiplied by deviation. Okay, let's compare these approaches. We have got that eta is equal to this formula, and let's replace the correlation or by definition on covariation divided on square root from product of variances. So as a result we take these formulas. The best linear approximation is the mean plus some constant multiplied on deviation. CUPED claims that the new time series is equal mean plus some constant multiplied on deviation. So we can see that CUPED it's just a best linear approximation in a Hilbert space of random variables on two random variables. First is correlated series and second is 1. So I wanted to show you, of course it's known for you, that the modern papers have actually been known a long time ago by people who work with fundamental science, and that the same results could be obtained much more easier. So thank you for your attention. I hope you were interested. If you have some questions about this report or statistic or A/B testing, you can find me at social network and I'll be glad to answer to your question.